Hi, I'm Felix. Did you know that it's easier for singers than instrumentalists to acquire absolute pitch? Let me demonstrate. If you sing from time to time, the following activity will not be challenging. The note on the bottom of the staff will move up and down with the pitch of your voice. Hum any note you feel comfortable with. Watch the note you sing on the staff and try to hold it in one place for a short time. When the microphone appears on the left side, begin humming your note. Okay, let's move the note you just sang to the left side. Now, hum the same note again. If you are a singer, you will likely not have difficulty repeating the same note. Okay, it is your turn again. Sing the same note. Now, let's compare the two notes. Very good. I ask you to repeat the same note in this activity, because consistency is a requirement for the next activity. I recognize your initial note as C#4. Now, instead of asking you to repeat that note again, I'd like you to hum the written note, C#4. Start humming this note. Now, let's compare the two notes. Very good. Congratulations, you have partially attained absolute pitch. One of the criteria for absolute pitch is, according to Wikipedia, ability to accurately sing a named pitch without an external reference. Maybe the pitch was not so accurate. Let's do a comparison. Instead of your initially recognized note, I will now display the note in standard notation. You were closest to it when you started the activity. Now, I will use the written notation, which means a note will always be on a line or in a space, not anywhere in between. In addition to the standard notation, I will put a red dot where the defined pitch or frequency for that note is located. Now, you see a green line towards your repeated note, which still has the red dot in the middle of the note. So, your note is displayed around the frequency you hummed. Now you see a blue line extended from your red dot towards the notated pitch. In this way you can see how much your pitch deviated from the notated pitch. If the lines meet exactly, you were within 20 cents of the notated pitch. In the Western music system, the deviation is expressed in cents. A deviation of 100 cents means a half step off from the notated pitch. A half step, or semitone, is the smallest possible interval, or smallest distance between two notes, as depicted in Western music notation. Here is your deviation in cents. Okay, do not worry if you were well off the mark. Consistency is more important. If you are able to reproduce one sound consistently, that is, to sing the same pitch without external reference, then you can use this pitch as a reference point to identify other pitches. Other criteria for defining whether one has absolute pitch, as listed in Wikipedia, are ability to identify by name individual pitches, for example the notes A, B, C, played on various instruments. Ability to name the key of a given piece of tonal music just by listening, without reference to an external tone. Ability to identify and name all the tones of a given chord or other tonal collection. Ability to accurately sing a named pitch without an external reference. Ability to name the pitches of common everyday sounds such as car horns and alarms. This is a fairly ambitious list of skills. You have already fulfilled the above list only for one criteria and one pitch. This is a good start. Now, say I ask you tomorrow to hum the same note again. You very likely will hum a pitch a whole note off or further from the note you hummed for this activity today. Perhaps either because you are in a different mood, or your vocal muscles are differently pre-tensed. Yet the note will likely still be near to the note you hummed today. This hit or near hit is a good starting point from which to acquire absolute pitch. And if you can sing a named note without external reference, it's not too difficult to acquire the remainder of the skills. The more complex tasks, like identifying the key of a given piece, or naming the notes of a given chord, are all based on the same listening skills. Singing a pitch accurately involves automatic listening skills. To solve the more complex tasks, in addition to the important listening skill, requires some knowledge of music theory. However, it is easier to feel the key than to find it through analysis. As you go deeper into the recognition process, you will start to hear intervals in chords. Finally, you will start to predict chords, because of the expectations from the chord progression rules. That is the point where you can feel the key. As you can see, you must improve the basic listening skills. If you are a singer, you can begin improving your absolute pitch abilities by turning your near hits into hits. In training these skills, relax or tense the vocal cords, so that the activity is independent of your mood or current stress level. In this way you can always produce the same pre-tension, and comfortably sing the desired note accurately, over and over again. This learned ability, or action, will automatically trigger the inner ear, since the brain will compare the outcome with the sound heard in your ear. If that sounds more like yoga than singing, it is, for a concentrated and relaxed state of the mind, allows you to control your muscles best. Like any professional athlete, you use your brain to focus on your goal. In order to get the best results, you have to remember, imagine, and aim ahead, so that your vocal muscles produce precisely the desired sound. Lesson 2, Instructions, will explain how you can improve your oral memory using the singing funnel method. But before you go on to that lesson, I'm going to tell you something. Everybody has perfect pitch. Let me prove it to you. Absolute pitch is related to a system of tuning notes in relation to each other. Western music uses the equal-tempered system, organized on a scale that divides an octave, a pattern of 8 pitches, into 12, equally measured, half steps. Thus every half step is 1/12 of an octave. However, there are many other tuning systems besides the equal-tempered, 12-tone system. For example, Wikipedia lists, among other systems, the following 3 tonal, equal-tempered systems: 19, 24, or 31-tone equal temperament. For these the octave is divided into 19, 24, or 31 equal steps. So, a 19-tone, equal temperament scale would look like this. Notice the additional steps in this scale, for the flatted and sharp notes. In addition, an interval other than the octave may be used to define the temperament. For example, here's a new, simpler system, the 2-note system. Actually, it is in 1-pitch equal temperament, and spanning the length of 4 octaves, but uses only 2 notes, a low note and a high note. To depict these notes in written form, we will use the same grand staff, used in the equal-tempered system, but only as a notation system. The 2-note system does not know any notes on lines or spaces. To distinguish the system further, I have filled the background with 2 colors, and only these 2-note symbols are available: a low note and a high note. If you did not hear the sounded low note, you likely are working on a laptop whose built-in speakers reproduce low frequencies inaudibly. To correct this, and if you are serious about ear training, you should connect a headset to your computer. Now let's do the test, and see if you have absolute pitch in my simple 2-note system. I will randomly play one of the 2 notes. Your task is to identify the note by clicking on the low note or high note. Listen to the note and then click the appropriate button. Excellent. I think you have got the idea. You have absolute pitch in our simple 2-note system. You can name the note without an external reference. However, in the next test I will play a note a whole octave away from the written pitches. Click the button of the pitch you think is nearest to one of the notated pitches of our 2-note system. This was not too difficult. The pitch position on the staff reveals that the distances to the notated pitches in our system are quite large. 3 octaves versus 1 octave. Arguably all frequencies nearer to the higher note, or those pitches that fall in the light yellow area, should be assigned to the higher note, and notes that are lower should be assigned to the lower note. The next test will be trickier. I will play a random note, which is only a semitone, or half step, higher or lower than the note in the middle of our two notated pitches. The middle note is 2 octaves away from either the lower or higher note. That means the note I play will only be a semitone nearer to one of our notated pitches. Can you still assign the pitch played to the corresponding note in our two-note system? Okay, was it just luck or were you really sure? In any case, to assign a pitch to a note name, not within the 12-tone, equal-tempered system, is also difficult for people who have absolute pitch. In fact, in some cases it will be impossible. Why? Let's take a closer look. If you sound a pitch of a notated pitch that lies exactly in the middle between two notes, then it is impossible to give one correct answer, since there are two solutions. Or if the sounded note is only a slight distance away from that middle frequency, say, only 0.0000001% higher than a quarter step, then, technically, that note belongs to the higher note, since the higher notated pitch, C#4, is nearer to the sounded pitch. In other words, the sound falls in the yellow band, which delimits the acceptable range of the note C#4. However, our ears are not built to differentiate between such small deviations. Therefore, if you recognize the situation, your answer might be, I recognize the note, and the pitch is neither nearer the next lower nor the higher note, but lies in between these two notes. We might introduce new pitches for sounds between the two notes, and narrow the colored bands around the frequencies of the notes. But this solution only shifts the problem. It then becomes, how do we define the border when identifying a pitch in between a newly introduced note and an old stock note? When do we assign it to one or the other? However, the identifying and naming process would be more precise, because we would introduce more possible answers in an octave than only 12 note names. Now, there would be 12 additional answers possible. For example, a note could be called in between C and C#. But then the same problem arises for the borders around these additional notes. Where is the point where we need not assign a sound to the note C, but instead assign it to the new note in between C and C#? Alright, back to our Western temperament, or equal temperament system, where the half step is the smallest interval. What does the above experiment tell us? Well, it gives us hints about what we have to learn to improve absolute pitch. The main instruction is to sharpen our listening skills in order to better differentiate between two notes. When you have to assign a note name to a pitch, the task is the same, whether you have small bands, as in the quarter tone sample, or broad bands, as in our two-note system. To illustrate the decision process, I will use the two-note system. Don't let you confuse that the separation line for the two bands lies on middle C. There is no middle C in the two-note system. There is only a high note, equivalent to C6 in the equal-tempered system, and a low note, equivalent to C2 in the equal-tempered system. No other notes are in the two-note system. Likewise, there are no notes on the separation lines in the equal-tempered system. The decision process goes as follows. You either have to remember the frequency of the line between the bands, and then you must decide if the sound is higher and has to be assigned the upper note name, or is lower and has to be assigned the lower note name. Or you must remember the frequencies of the lower note and the higher note, and then you must decide to which note the sound is nearer. In identifying pitches, we are accustomed to listening to the pitch played on a piano or other distinctly tuned instruments. It is easier to remember the pitches of notes we hear all the time than the frequencies that separate pitch bands. which are the flipping points for the decision to assign a sound to a particular note name. However, ear training with the piano is not very efficient, in that the piano is tuned to half steps and cannot produce pitches in between. To train the ability to better identify pitches that are not in tune with the equal temperament, we need an instrument that can produce pitches in between distinct half steps. A good instrument is our voice. If we haven't developed absolute pitch yet, we likely are off the notes. Therefore, the solution is, learn to sing accurately. That means you have to learn to recognize pitch deviations. In order to sing accurately, it is best to conceptualize a note in your head first, before you attempt to sing the note. In other words, listen to your inner ear. Once the pitch is in your imagination, you have to adjust your vocal cords to produce the desired sound. To improve your inner ear, you must have external feedback that guides you in the right direction. To evaluate your inner ear, you will express your conceptualized pitch by adjusting your vocal cords in before and while singing. The external feedback of our method will tell you how precisely you can remember and reproduce a tone. To gain absolute pitch, you have to remember the pitches accurately. By gaining control over your voice muscles, your mind enables you to hit the pitches of the notes with precision. So, by combining the two pillars of absolute pitch, consistency and precision, and using our system, the best we know for memorizing, we have developed the following solution for training in absolute and relative pitch: the Listening Ear Trainer. Continue with the next lesson, instructions.